Hi, hello everyone. Hello, my Cairo University Communication and Electronics Engineering Department graduate students. I wish you all are doing very well. I would like to start by thanking you so much for the amazing engagement and the questions from your side during our live lecture conducted 2 days ago. And I wish you find this recording of it useful to you. So please let me start by sharing my presentation with you. So today we will continue speaking about our topic of clustering. And for anyone who is watching this recording online, my name is Hesham Eraqi, and I am a senior expert of AI and deep learning at Vallejo. And I am an adjunct faculty at the Computer Science and Engineering department at the American University in Cairo. I have left here my emails. Please, if you have any questions, please send me an email and I will be more than happy if I can provide you with any help. So during our last week, we started by discussing the different types of machine learning algorithms. And actually, we have 3 different types of machine learning algorithms. We have the supervised machine learning algorithms, we have the unsupervised machine learning algorithms, and we have the third and last type, which is reinforcement learning. Since the start of the semester, we have been talking about supervised machine learning algorithms. And since the last week lecture, we started to cover clustering algorithms as example for unsupervised machine learning algorithms. Today, we will continue talking about this topic also. And because the third type, which is the reinforcement learning, is not very heavily covered in our course. So during our last week lecture, we covered quickly 2 types of or 2 examples of reinforcement learning algorithms, which are the Q-learning algorithm and the evolutionary neural network. Okay, so today we will continue talking about clustering algorithms. Last week we covered the k-means algorithm, which is a distance-based clustering algorithm. Today we will talk about density-based clustering, hierarchical clustering, and soft clustering. And eventually we'll talk about the clustering validation topic and how can you judge numerically or quantitatively if the output of the clustering algorithm is good or bad, especially if you have data that is high dimensional that you cannot visualize. Okay. Again, this is our reference book, so I encourage you to read about the topics we discussed from this very useful book. Okay. So before starting talking about our first type of clustering, the density-based clustering, I would like to discuss very quickly something related to our previous week assignment. The first question was asking you if you have a k-means algorithm, and for initializing the centroids, you rely on the strategy of picking the random initial centroids from the data points. If you use this strategy, and assuming that you pick up k equal to the true k, or the ideal or the ground truth k value, and in your data you have your clusters having around equal points, what is the probability, if you follow up this initialization strategy, what is the probability of having your initial random centroids lying in unique true clusters? Okay, we say that this probability should be very low, and this is why this method is not very successful, and k-means plus plus is better. And many of you are jumping to the conclusion that the probability is equal to factorial k over k to the power k, which is absolutely correct. And this value is going to 0 very quickly if k is large. But I would like you, if you jump to this conclusion directly, I would like you to indicate how did you calculate it. Okay, so in your submitted report, if you didn't indicate how did you calculate it, please edit your report and send it back to me, please. Okay, so let's go for the density-based clustering algorithms, our first topic of today. So as a very famous example for density-based clustering techniques is DBSCAN algorithm. So DBSCAN stands for density-based spatial clustering of applications with noise. Generally, the density-based clustering algorithms can discover clusters of arbitrary shape as long as this shape maintains the same density of points. This is a very good advantage. It will be clear later on when we compare the results of DBSCAN algorithm with k-means algorithm. But an advantage of DBSCAN algorithm specifically is that it can detect noise. It can filter out any noise or outlier data points in your data and will not assign them to any of your clusters, but it will filter out these points. It will tell you these are noise. They don't belong to any cluster, okay? And for sure, k-means clustering algorithm is not able to do this. And to be able to filter out these noise points, the DBSCAN is taking two input parameters from you. It takes the epsilon and the minimum number of points. Epsilon is the search distance around some point for other points that belong to the same cluster. And the minimum number of points is actually the parameter that is used to define the noise clusters. Okay, so before going into the details of DBSCAN algorithm, how it works, let's very quickly discuss two concepts. Okay, so this is the first concept. So you should be able, using epsilon and the minimum number of points values, to classify each point in your data into being high density point or low density point. Okay, so for example, if you have point P and you want to decide whether it's high density or low density, you create a circle, okay, around that point, and the radius of this circle is epsilon, and you check if inside this circle how many points are there. If the number of points inside the circle is greater than or equal to minimum number of points, so that point is classified as high density point or a core point. Okay, so it is the same. It is different names that are describing the same thing. So let's, for example, by the way, P here is high density point if this is the epsilon value, and if minimum number of points is 4, for example, because here we have 4 points inside the circle, which is less than, which is greater than or equal the minimum number of points if it is equal to 4. So if minimum number of points is equal to 4, what about Q point? Is Q point a core point, a high density point, or it is low density point? Let's construct a circle from Q. And for this circle, how many points do we have inside? We have 3 points, which is not greater than or equal minimum number of points if it is 4. So Q is low density point. It is not a core point. Okay. The second concept I would like to highlight before going into the details of the DBSCAN algorithm is the concept of density reachability. So here we have 3 sub-concepts. A point Q might be or not directly density reachable from another point. Another concept or sub-concept is indirect density reachability. And the third sub-concept is that 2 points might be density connected or not. Okay? So the first 2 sub-concepts, so the density reachability is not symmetric, it is asymmetric, we will know how, but the density connectivity is symmetric. So if you have a point that is directly reachable from another point, it is not guaranteed to be as other way around. Okay, this is for the direct density reachability, and the same for the indirect density reachability. Okay, and when we say density reachability, so by default we mean indirect density reachability. But what about density connectivity? If you have a point that is density connected to another point, it is the other way around. So density connectivity is symmetric operation, but for the density reachability, it is asymmetric. Okay, so when can we say that Q is directly density reachable from another point P? When can we say this? If 2 conditions are verified. If you can say Q is directly density reachable from P if P, the second or the origin point, is a core point, and at the same time Q is a direct neighbor of P, which means that it is lying at, when we say Q is a neighbor of P, it means that if you create a circle centered on P, having a radius of epsilon, you will find that Q is inside this circle. Okay, so Q is directly density reachable from B because B is a core point and Q is a neighbor of P. But why P is not directly density reachable from Q? Because Q is not a core point. So the first condition is not verified. So despite that B is a neighbor of Q, but Q is not a core point, this is why B is not directly density reachable from Q, but the other way around is true. Okay, what about indirect density reachability or density reachability? Q is density reachable from P if you have a chain of directly density reachable points in between them. Let's imagine this example. So for sure, P is not directly density reachable from Q. Q is a core point in this example, but P is not a neighbor for it of Q. This is why it is not directly density reachable from Q, but you will find that it is indirectly density reachable from Q, because you have a chain of points in between, which is in this case a single point, that yellow point. The yellow point here is directly density reachable from Q, and P is directly density reachable from the yellow point. So we can say that B is directly density reachable from Q, okay? But again, it is not the other way around. The yellow point is not directly density reachable from B, okay? So B is this density reachable from Q. It is not directly, it is indirectly, okay? But not the other way around. Q is not density reachable from B, okay? So what about density connectivity? So if you have 2 points, P and Q, and you are checking whether they are density connected or not, if you have any point in the middle where P and Q are density reachable from that point in the middle, so P and Q are density connected. If you don't have any middle points that verifies this, so they are not connected. So in this example, B is not directly reachable from Q, because here it seems that Q is not a core point. The same is true. Q is not directly and is not indirectly density reachable from P, okay? But you will find that P and Q are connected because Q is density reachable from O, B is density reachable from O, so we can say B and Q are density connected, okay? So this is the pseudocode for the DBSCAN algorithm, and the DBSCAN algorithm is classifying each point as either a core point or a border point or a noise point. If it is a high density point, it's a core point. If it is a low density point, it can be a noise point or it can be a border point. By default, it is a noise point. But if it is a neighbor of a core point, if it is a direct neighbor of a core point, it is classified as a border point. So for example, this point here is not a core point. This is why it is a noise. And it is not neighbor to any of the core points. This is why it remains noise. But for these yellow points here, they are classified as border points because they are not core points. But you will find that this point here is a neighbor to that core point here. So it's a neighbor to a core point. This is why it is classified as a border point, okay? And this is the pseudocode for the DBSCAN algorithm. So it rates all of your data points, whatever the data structure you used to store your data points. And for each point that is not yet classified, it classifies it, okay? So for each point O belonging to your data, if O is not yet classified, let's say classified, okay? if O is a core point, let's collect all the points that are density reachable from it and assign them to a new cluster. Okay? If O is not a core point, it will be assigned as noise. Okay? So let's imagine, for example, we started from this point. This is O. So O is not a core point. It will be classified as noise. And let's assume that point was a second point to inspect. So in the second iteration of the for loop, this is O. And we have only one point that's classified so far, which is that yellow point. We classified it as noise. And in the second iteration, this is O. This is the point O. Is it a core point? Yes, it's a core point. So let's collect all the points. Let's loop over all the points. Okay, classified and not classified, and check whether they are density reachable from O or not. So this is density reachable from O. This is density reachable from O. This is density reachable from O. This point is also density reachable from O. This is the same. This is the same. This is the same. So but this is not density reachable from O. So all of these points during the second iteration of the for loop will be classified as our first new cluster. Okay, so during the first iteration of the for loop, that yellow point was classified as noise, but that was corrected during the second iteration, and it was classified as the first cluster we have. Okay, and after this, you will find if this is the third point in your data structure. So you will find that the if condition is not verified. It's classified already as the first class. If this is the point after it, it's classified already. This is classified, this is classified, this is classified. The only point that remains to be classified is that point. So at some moment in the for loop, you will have this point as your O. And is it a core point? It is not classified yet. So the inner if condition will check, is it a core point? No, it is not a core point. So it will be assigned as noise. So eventually, if epsilon is set to that value, okay, indicated graphically here, and minimum number of points is indicated as 4, you will find that the DBSCAN will tell you that I have a single cluster in my data, and that point does not belong to that single cluster, it is noise. So the DBSCAN can automatically, from the epsilon value and the minimum number of points value that you predefine, that you preset, determine how many clusters are there in the data, which is a key important advantage for using DBSCAN or density-based clustering techniques in general versus the distance-based clustering techniques like the k-mean algorithm. Okay, so, and here I have a very interesting question for you as an assignment that you should deliver before our next week lecture, inshallah. I would like you to calculate the runtime complexity of the DBSCAN algorithm and the space or storage complexity. Okay. You might think that it is not a very relevant topic to machine learning, but it is very important as a machine learning engineer or as a data scientist to be able to calculate the complexity of your algorithm, because it can be a very important criterion that help you prefer or favor some algorithm over another one. It's very important. And you can report either the upper bound complexity or the low, at least you should report the upper bound complexity, because we as engineers are interested on the upper bound, that actually what will happen actually will not exceed that upper bound. But also you can optionally report the lower bound and the tight bound, but at least you should be able to report the upper bound complexity analysis, or in other words, the big O notation. And please note that if you report the upper bound complexity, it can be for the worst case, it can be for the average case, it can be the best case. So you might be reporting the upper bound of the best case, the upper bound of the worst case, the upper bound of the average case. So as optionally, you can report all of them, but as engineers, we are interested in the worst case. So at least you should report the upper bound of the worst case scenario that can happen in some data you have. Okay, very good. So if you have data points like this is how the DBSCAN algorithm will choose the core points and the border points and outliers. In this graph here, core points are in green, border points are in blue, outliers are in red. Okay, so it is very nice that the DBSCAN was able to isolate the noise points. Okay, and actually this is the epsilon value and the minimum number of points values that was used to obtain these results, which is I take it from this reference. And this is the actual clustering results that you will get using the DBSCAN algorithm. It's very nice. So given the fact that you have completely different arbitrary shapes for each cluster, the DBSCAN handled it very smartly, and moreover, it was able to isolate the noise points for you. Okay, so so this is a nice comparison for the results achieved by running the k-means clustering algorithm and the DBSCAN clustering algorithm on the same data. And for all the examples, k-mean, the k-value is set to 2, and for DBSCAN, the epsilon is set to 0.1, and the minimum number of points is set to 3. In the first example, the k-means is forced to split your data into 2 clusters because k is equal to 2, which is actually equal to the true value. But the data nature is not suitable for the k-means algorithm because k-means algorithm is assuming that the data is the same cluster data is separated in a spherical bulk or a circular bulk. Okay, there is no overlapping that's happening between your different clusters. Okay, so it assumes that this is the first center that the k-means is detected. This is the second center, and it assumes that the first bulk is centered around that center. This is your first class, and that your second class, which is a very bad clustering outcome. But the DBSCAN clusters the data actually very good. These are the 2 clusters you have. And the same is happening for the second example here. This is the result from the k-means. It's not good for the same reason. And this is the clustering you get from the DBSCAN, which is very good. And in the third example, actually, the data is very suitable for the k-means algorithm and the DBSCAN algorithm. But because you didn't set a proper k value, which is a fact that you don't have access to. If I ask you beforehand what is the true k value, it is normal that you don't know it. Okay, so the true k value here seems to be equal to 3, but you set it to 2, which is something that's very normal. It should happen a lot. If you use k-means, you will not be able to set k equal k true. So by setting k equal 2, k-means is forced to distribute your data into 2 clusters, but DBSCAN is able to detect that this time you have 3 clusters, and these are the 3 clusters you have, each cluster in a different color. Okay, so DBSCAN can cluster your data into 2 clusters or more than 2 clusters, and it can detect how many clusters are there. Okay, for the fourth example, you have almost uniformly distributed data. K-means still split them into 2 clusters, and you might run k-means again. You will find the result is completely different. You might find that the first centroid is to the bottom of this data view, and the second centroid is to the top, and you will find that the data are splitted horizontally, not vertically. It depends on how your random initialization is working, as we have discussed before. But the DBSCAN can detect that the data is belonging to a single cluster, despite the fact that you didn't change the epsilon value or the minimum number of points. But if you want maybe to get a more detailed answer from the DBSCAN, if you want to the DBSCAN to classify each bulk of these small bulks into a separate cluster, you might change the epsilon and the minimum number of points values to achieve these detailed results. And we will talk later on about how can we set the value of epsilon and the value of the minimum number of points. So the advantages again of the DBSCAN algorithm is that it can detect noise and outliers, and you don't pre-specify the number of clusters. It automatically detects the optimal number of clusters for you given epsilon and the minimum number of points, and it can handle clusters of different shapes and different sizes. Okay. Actually, the DBSCAN algorithm is the most used clustering technique in automotive, at least from what I know. It's very efficient if you want to cluster the data coming from a laser scanner or a LiDAR sensor to do this clustering with DBSCAN algorithm. Okay. Very quickly, what is a laser scanner or a LiDAR sensor? It's a proximity sensor, like radar sensor, like ultrasonic sensor. It tries to transmit some signals and receive back the same signals to estimate the distance of the objects in the environment or the obstacles in the environment relative to the sensor itself. To do this, the radar sensor is transmitting sound waves, but the laser scanner is achieving the same task by transmitting laser beams. So a laser scanner sends a laser beam in some direction and records the time of transmission. And this beam will eventually hit an obstacle and being reflected back again, and the sensor receives it and records the time of the reception of such echo or such beam. And by having the transmission and the reception time, the beam round trip time is calculated. And because we know the speed of light, we can estimate the distance between the sensor and the obstacle, and we can represent this in the 3D space by a dot that tells us there is an obstacle at this location. Actually, the laser scanner is sending several beams, and the angular difference between the beam and the neighboring one is very, very small, because the laser characteristics allow us to do this while not having so many interference between the different beams. This is not, for example, achievable if you are going to rely on a sonar or a radar or an ultrasonic sensor. So the laser scanner beam, if you try to visualize what's happening in top view, usually you have a car here and you have your sensor here, and your sensor is actually transmits so many beams like this. Most probably this is a road. So you have a curve here and you have another curve here, and it seems that the road is something like this, and the vehicle is here, and the vehicle can turn in this direction. This is what I can see from the figure. All of these reflections are coming from the ground or the road, because you might have some reflections from the road itself. This reflection most probably is coming from a car. These reflections most probably are coming from some traffic signs on the sidewalk, and this reflection for sure, this L-shaped cloud, is for sure coming from a vehicle, because you have beams from your sensor that hits the vehicles from this direction. This is why you receive an L-shaped cloud. But if the vehicle is just in front of you, something like this, you get U-shaped scan points. Okay, that's clear, all of this. So this is a top view cloud of points that are received from the laser scanner at some moment. Okay, if you give this cloud of points, you don't have ground truth for all of these points. Beforehand, you will not be able to tell whether these points are belonging to the same object or not, okay, the same cluster or not. So you give it, for example, if you want to count the number of objects in the environment, you can give it to the full scan, the DBSCAN algorithm, and it will tell you it will do the clustering for you, and from the clustering you can count the number of objects that are in space. You might take the points belonging to this cluster, for example, and send it to a machine learning classifier to classify it, so you know whether it is a vehicle or road or bicycle or a pedestrian or something like this. Okay, so this is why a DBSCAN algorithm is very useful in classifying LiDAR data or clustering LiDAR data, and the result is something like this, which is something that's very that's quite good. And to achieve this result, we used epsilon equal 2 and minimum number of points equal 50. If you decrease the epsilon value, you will find that, for example, the algorithm decided to separate these points here from all of these points into two separate clusters, but before reducing the epsilon, they were the same cluster, which seems not a good choice. So reducing the epsilon is proven to be very useful in this case, but unfortunately there is no free lunch. So you had a single object here. Most probably these are reflections that are coming from a tree, and it was one solid cluster when epsilon is equal to 2. But when you reduce the epsilon, you find that the single cluster started to split into several clusters. Here you started to have some points from the vehicle classified as noise, and this is the disadvantage you obtain. So you gain some improvement and you lose so some clusters that are merged by mistakes are unmerged, which is good, but you have some classes that started to lose some of its data points to another class or cluster or class, or being classified as noise. Okay, this is a strong indication that the correct epsilon value is something in between. So an epsilon value between 1 and 2 should be better than both. Yes, and when we try epsilon equal 1.5, you find that it's doing good here and it's doing good here, and the vehicle here is still one object, one cluster. It is not split into several clusters. So this is a heuristic that might help you to determine the value of epsilon by trying different values until you settle on the right value. But anyway, one major disadvantage of the DBSCAN algorithm is that it is very sensitive to the parameters. So these are two outcomes from the DBSCAN algorithm. Each time I set the parameters differently, but I'm using the same data to be clustered. For the first time, I use epsilon equal 0.5. For the second time, I use epsilon 0.4. And for both times, minimum number of points is equal to 4. And you can see by doing a very slight change in the epsilon value, you end up having completely different clustering decisions. So the algorithm is very sensitive to epsilon. Also, in the second example here, the minimum number of points is 4 during the 3 times, but the value of epsilon is changing at the first image. At the first result, the epsilon value is 5, the second is 3.5, the third is 3. So by doing slight changes in epsilon, you end up having completely different clustering outcomes. So one disadvantage of the DBSCAN algorithm is that it is very sensitive to the parameters. Another thing is that don't expect that the DBSCAN will be able to handle a problem where you have your data distributed into clusters that have separate densities. Okay, because it's a density-based clustering technique, and it assumes that all of your data are almost having the same density per cluster, okay? And that density per cluster is described by your choice of the epsilon value and the minimum number of points value, okay? By setting minimum number of points to 4 and epsilon to 9.92 and running the algorithm on that data, we can obtain that result here. Okay, it's not very bad, but when you do very slight change to the epsilon value, so it becomes 9.75, as you can see, we obtain a completely different clustering outcome. Okay, so this is a very major drawback of the DBSCAN algorithm, and also it motivates the idea that we need a proper method to be able to estimate the value of epsilon. This is a very nice method that allows you to estimate epsilon given some value set for minimum number of points. Okay, so to make the concept more clear, let's discuss some example. Imagine that all of us are points that belong to the same cluster. Okay, so each one of us is a point, and all of us are points that share the same true cluster. And if I ask each one of us that question, what is the distance between you and your third nearest neighbor point? You will find that almost all of us will give almost the same distance because we are points at the same cluster. But if you do the same exercise for points that are noise, they are not belonging to a cluster, you will find that the distance is much higher, and from this we can know to which value should we estimate the epsilon. So let's have all the data points coming from all the clusters, coming from noise, the points that we want to cluster, and let's firstly, we need to pick up a value for the minimum number of points. Let's pick up 4. It's better to pick up a value that is reasonable based on your understanding about the data. So let's assume that we picked up minimum number of points equal 4. And using that assumption, we want to calculate a reasonable value for epsilon. So we will sort all of the input points according to their force, because we said minimum number of points equal 4. So we will sort all of the points according to their force nearest neighbor distance. Okay. So for each point, I will calculate the distance between it and its force nearest neighbor. I will record this number. I will do this for all the points. Then I will use that number to sort all the points. So the point that has the smallest distance to its force nearest neighbor is that point. Afterwards is that point, and so on. Okay. So you will find that there is a value that all the data points tend to agree on, which is around 5 in this example, except for the outlier or the noise points, which tend to have a much higher distance to its force nearest neighbor. And using this, you can decide to set your epsilon to be something between that settled value of 5 and that moment where some exponential growth is happening. So an epsilon around 10 is a reasonable choice in our case. Okay. The third type of clustering algorithms that we are going to cover is the hierarchical clustering. And the good news about hierarchical clustering is that it does not assume a particular number of clusters. So it does not ask you for k, unlike k-means. This is a good advantage for hierarchical clustering. But on the other hand, the major disadvantage for it is that it is too slow. The runtime complexity for hierarchical clustering is big O of n squared log n. We will discuss later how we calculate it. And the space complexity also is non-linear. It is big O of n squared. Okay, so this big O n squared log n is the upper bound complexity at the worst case. And the idea behind the hierarchical clustering is much simpler than the DBSCAN algorithm. So initially, it assumes that each point is a separate cluster by its own. Okay, this is the first clustering configuration that the algorithm reaches. And this configuration is stored. And the second step is to group the nearest two clusters or merge them into a single cluster. So it seems that these two clusters are the nearest, so they are merged in a single cluster. So we end up having 5 clusters only instead of 6. This is the second configuration, and we store it. After this, we merge the nearest two clusters, so we end up having 4 clusters. This is the third configuration. We store it. After that, we keep merging the nearest two clusters. This is why we need to think of a criteria to measure the distance between two cluster of points. Okay, it is very important, and we have different criteria to do this until eventually we merge all of the points into a single cluster. This is the last configuration we reach. Okay, and you start by looking to this last configuration we reached and ask yourself, is it good? Either you can judge the quality of the clustering visually, if you can visualize the data, or by relying on any of the clustering validation techniques that we are going to discuss at the end of today's lecture. If it is good, okay, so your data is one cluster, like it can be a good answer to have your data as a single cluster, like the example we had before, where you have a uniformly distributed data. Okay, and if the result is not good, you go back one step. So you check the configuration of having 2 clusters. If it is good, use it. If not, go one step back and check the configuration having 3 clusters. If it is good, take it. If it is not good, don't take it. Okay, and if you check any configuration out of all of these configuration, let's imagine the second configuration we have here. Once the hierarchical clustering did the decision that your 5 clusters are like that, these 2 points are one cluster, this 1 point in one cluster, this 1 point is a third cluster, and so on. This decision cannot be undone, unlike the k-means expectation maximization algorithm. Okay, so you can think of this as a minor disadvantage of the hierarchical clustering. Okay, this is another illustration for what's happening, and you can encode all of the mergings that are happening and the distance between the merged clusters in a diagram like this. The distance is included in the vertical axis, and you indicate the points of your data on the horizontal axis. This is a very useful diagram, which is called the dendrogram. Okay, and using this dendrogram, you can, by the way, pick up the right configuration that you should use. So initially, it seems that B and C are the nearest 2 clusters. So initially, you have all of your points as separate clusters. Okay, and at the second step, the first merging that's happening is finding that the cluster B and the cluster C are the nearest 2 clusters, so they are merged into one cluster, BC, and the distance between them are indicated here, if you can see my laser pointer. Okay, and after this, you will find that in the third step, the 2 nearest clusters are D and E. Okay, so they are merged, and the distance for merging D and E is like this. Please note that this distance for merging D and E is a bit higher than merging P and C. Okay, and afterwards you will find that merging the F cluster with the DE cluster is a choice that gives you the two clusters with smallest distance between each other. So you merge them, and the distance between them are like this, okay? And you keep doing this until you have two clusters, cluster A and the cluster B, C, D, E, F. And you merge this cluster B, C, D, E, F with A cluster until you have a single cluster, okay? And this is a nice diagram that shows the hierarchical clustering outcome on different sample inputs. So this is the outcome for the algorithm given these data points, and this is the corresponding dendrogram. And for these data points, that was the corresponding dendrogram. So it's performing very well. Hierarchical clustering is performing very well in this case, and in that case, not very well in this case, not very well in this case. It performs very well with that case as well. And so again, like DBSCAN, like k-means, it has advantages, it has disadvantages. It might suit some type of data, it might not suit another type of data. We will compare actually it against DBSCAN and the k-means later on. And for sure, when I visualize something like this in the second example, I mean that we draw the dendrogram, we executed the hierarchical clustering until all the data is clustered into a single cluster, and we started from this asking ourselves, is it good result? We found that it is not a good result. We checked the configuration before the last, the one that's having two clusters, we found that it is much better. So this is why we have taken it, okay? This also, that choice also can be guided by making use of the dendrogram. Because if you look to this dendrogram, you might very clearly see that the last merging process happened at a very large distance, which means that you have two clusters that you want to group into a single cluster, but the distance to do this merging was very high. So it seems that the merging decision was not very wise, okay? So let's neglect this configuration and check the configuration before the merging. Is it good? It seems visually it is good if you visualize it. If you use any of the metrics that we are going to discuss for validation, you will find it is good. If you check the dendrogram by your eye, you will find that it is not a very good idea to split this second cluster further into more clusters, because the distances of merging are not relatively very high, okay? Again, here you have a very large distance at your dendrogram, which indicates that you should not take the last split, but the one before the last, the configuration before the last was very good. And also the configurations before it are not good because the merging for them happened at relatively small or equal, almost equal distances, okay? So it is very good to know where to cut, where to stop, where to trace back. And for sure, if you ask me about an ideal formula to tell you where to cut, there is no definitive answer. At the end of the day, when you are doing cluster analysis, there are often several good solutions, and they are equally good from theoretical point of view. So the dendrogram is some mean that allows you to do the cut more properly, or to select the number of clusters more properly. But at the end of the day, there is no golden rule to follow, unfortunately. In order to calculate the distance between two clusters, we have different criteria to achieve this. And if you have two clusters, it's like having two disjoint sets of points. You might search for the closest pair of points and then calculate the distance between them, and you can use this distance as an indication of how far or close the clusters are from each other. If you do this, you are using single linkage hierarchical clustering, and you can solve this problem of finding the closest pair of points in these two disjoint sets of points using the KD trees, the KD binary search trees, and you can achieve this or calculate this in a time complexity of big O of n log n. Because you need to calculate the distance between, in the worst case, n number of clusters, where n is the number of points in your data, so you need to execute this operation n times. So you have an operation that's costing you big O of n log n. You repeat it n times in worst case. So this is why the runtime complexity of the hierarchical clustering is n squared log n. Okay. So if you take the closest pairs distance, this is a single linkage hierarchical clustering, but also you can rely on a different criterion, which is you might search for the farthest two points in the two clusters, calculate the distance between them, and you can take this as your criterion for this as a distance between the two classes or two clusters. Again, each approach has its advantages and its disadvantages, as we are going to discuss in the coming slide, but there is no one that is better than the other one in absolute. Something in between is the average linkage hierarchical clustering, and it tries to calculate the average distance between a point in a cluster and all the points in the other clusters. Okay. The last method is the word method. If you follow the word method, firstly you need to calculate the centroid point of the points in cluster 1, and you calculate the centroid point in the centroid point for the points in cluster 2, and the centroid point for all the points in cluster 1 and cluster 2. And using these three centroids, you can calculate the word score or the word distance. Initially, you keep adding the square of distance between each point in the two clusters to the global centroid between the two clusters squared. Okay, so the distance between that point and that centroid is C1, this is C2, C3, and so on. I do this for the two clusters, and you add the square of this CI. We take the square to give more weight in the distance to large distances. Okay. And in order to normalize these distances relative to how much the clusters are compact, we subtract the value we obtained so far by doing the following. For each cluster, you calculate the distance between each point in the cluster and the centroid of the cluster, which is A1, A2, A3, and so on. And you do the same for the second cluster. You get B1, B2, B3, and so on. And at the end, you do it like this. You subtract A1 squared minus A2 squared minus B1 squared minus B2 squared, and so on. Sorry, the equation had some mistake and I corrected it. Okay, so it is something like this, and this value here is giving you a small number if the clusters, two clusters are more compact and less separated, and it gives you a higher value if the two clusters are more separated and or more or less compact. Okay. So one advantage of the single link clustering is that if you have a large gap between the two clusters, like in this example, you can very easily separate them, even if you don't have elliptical or circular shaped clusters like this. One disadvantage for the single link hierarchical clustering is that it cannot properly cluster the noise between two clusters, either into a separate cluster or either as one of the two clusters. The good thing about complete link is that it handles the noise better. Okay, so as you can see here, the points in the middle were not scattered between the two classes. They were classified into one cluster of the two, which is better than the single link. And actually, the average link and word is sharing the same advantage. One disadvantage of the complete link is that it tends to break large clusters like this, and like the average link and the word methods, it is more biased towards spherical clusters. And when we say that if you have 2 points and you want to measure the distance between them, by default, we always assume that the distance are the Akkadian distance. So assume that you rely on single link. So between the two clusters, you try to detect the closest pair. These are the closest pair of points detected. So we want to calculate the distance between them. So the function d, by default, people tend to think that d is the Akkadian distance. But in some other applications, we might have other distance metrics that are more suited to as application in hand. Like, for example, if you want to go from city A to city B, assuming that each data point is a city on a map, it is better to use the Manhattan distance that describe more the road network instead of relying on the Euclidean distance, which actually is not practical because you don't have a mean to go from that city to the other city just directly like this, but you have some routes to follow. Okay, so there are different types of distances that you can use. Today, now we will discuss a quick coding exercise about how can you implement hierarchical clustering using Scikit library on Python, and how can you draw your dendrogram. Okay, so we will open Google Colab, colab.research.google.com. You will open a new notebook or upload the notebook that I will be sharing with you. Let's open our notebook. So from Scikit cluster hierarchy package, we import the dendrogram and word and single classes. Yeah, I think we don't use word in this code. We use word, but we don't use single. You can, but here I'm showing you how you might import the different kinds of hierarchical clustering. We load the data sets from Scikit-Learn and plot, because we are going to plot our data. We load the iris dataset, and again, it is a dataset composed of 3 different classes of flowers. So as you can see here, you have 3 different classes of flowers. This is the label, and for each data point, for each image, for each sample, it has a label. It has, for sure, this is a single image for a single flower. So it has a single label, okay? But for this image, we calculate some features, okay? For the flower, we calculate what's called the petal the betal, and the sepal. So these are the features. We have 4 different features from each image, and we have one label out of 3 possible options. We load this data set. We load only 10 samples only, and the first 10 samples only, and we plot them. As you see here, when we plot them, I plot them and I give them the color as the target class. Okay, so all of the 10 data samples we have are belonging to the same true label or true cluster. And if you increase the amount of points, let's run the import first and see what is the effect of increasing the number of data points that we load from the data. So let's run this again. So you'll find that we have 2 classes only, but if you start to increase further, you will start to take data from the 3rd class. So, okay, so you have here 3 colors corresponding to 3 classes, but here I take only 10 to let you see the dendrogram and be able to see it more clearly. So we run word clustering, hierarchical clustering on our data, on our 10 data samples. You get what's called the linkage matrix, and that linkage matrix object, you can give it to the dendrogram API, which we import also from Scikit cluster hierarchy, and it will draw it for you if you just plot show to have your figure. So if you run this, you will have your data clustered and you will have your dendrogram drawn for you. Okay, so if you increase the amount of samples, you will start to have more data points. Okay, and you will find that your dendrogram is more complex. Okay, and it's very simple to run hierarchical clustering using the Scikit library. So as an assignment for you, please do run hierarchical clustering on 10,000 samples from the dataset. And I would like to see the result of the clustering and to compare it with the ground truth. So we have the ground truth. I would like to see your outcome from the clustering based on where did you decide to put the cut and how to do this in terms of programming. Please check how to do this. It's not very complex, and compare the outcome with the ground truth and try to comment about what you reach. Okay, so this concludes what I wanted to say regarding hierarchical clustering. The last type of clustering techniques that we are going to discuss is the soft clustering. And from its name, it is trying to assign each point to some cluster softly with a probability. So it tells you this point is belonging to cluster 1 by probability X, and it belongs to cluster 2 by another probability Y. So it tries to do it in a soft way instead of doing hard assignation, as the case was with all the discussed clustering algorithms so far, right? So if you give the k-means algorithm this data and you predetermine k equal 4, you will get an answer like the one shown here. And for example, a point here in the edge of that blue cluster should be assigned less strongly than the points in the middle to the cluster. But k-means does not do this. It does hard assignation. So each point is 100% assigned to one cluster. Unlike k-means, the GMM is doing soft clustering. So beforehand, you also need to determine or give the value of k. the number of clusters that are in your data. And according to this, the GMM clusters your data, and this is the outcome you obtain. If you define k equal 4, like in this example, you get for each point a score that tells you how much it is classified as blue, and another score that tells you how much it is classified as green, another score that tells you how much it's classified as yellow, and so on. So, for example, this point will have a very high score to be assigned to the blue cluster compared to the other points, and compared to the points in the edge. Okay, and that point in the edge here will get almost equal weights or scores of assignation to the blue cluster and the yellow cluster. Okay, because it is in between. It is higher score for the blue. This is why it was assigned at the end of the day to the blue, but the confidence was not very high. Okay, and the same for this point. The more the points tend to be in the core of the cluster, the more the weight or the confidence of assignation will be. And if you give as a Gaussian mixer model data like this, you will find that the same is happening. So it does not assume by default circular clusters, but at least assumes it is elliptical clusters. Okay, so it can give you something like this, which is a very good clustering outcome. So this is a high-level idea. Let's dig into the details and how this is happening. So now let's quickly revisit what is the meaning of a Gaussian distribution or a normal distribution. If you have some data and you decide that your data are following or can be modeled using a Gaussian or a normal distribution, you calculate the mean value and the standard deviation of your data points. If your data is 1D, you have an equation to calculate the mean value and another equation to calculate the standard deviation given the mean you have calculated and for your data point given your data point, and you obtain a mean value, let's say of 100, and you obtain a standard deviation value, let's say of equal to 5. You find it like this. What does this mean? This means that 90% of your data are scattered. This means that all of your data are scattered around the mean value of 100, and 95% of your data are either between 100 minus 5, minus the standard deviation, and 100 plus 5. So 95% of your data is between mu minus sigma, standard deviation, and mu plus sigma, or the mean plus the standard deviation. Okay, so in 2D, if you have data points like this, assume that I collected the data from the NBA players, the American basketball league players. Okay, and for each player I record two features for him: what is his height and what is his maybe weight. Okay, so you will find that the data, each point here is representing a data point. X is height, Y is weight. Ignore the numbers here. They might be after scaling with some normalization factor or something like this. But these are the data points or the players that I have. Okay. So this is a 2D data. It's not 1D anymore. So when you calculate the mean value, the mean here is not a scalar. It's not 100 like the previous slide. It's a vector of two numbers. So you have a mean value for the height and a mean value for the second feature, which is the weight. So you have a mean vector. What about the standard deviation? By the way, the square of the standard deviation is the variance. Okay. So for 1D distribution, you have variance which is a scalar value, single number. But in 2D, you have a matrix, which is called the covariance matrix. So mu here is the vector of the mean, and sigma is 2 by 2 because we have two features. It is a 2 by 2 symmetric matrix. It's always symmetric as a covariance matrix. And actually, the diagonal is indicating the variance of each features. So the 1 and 1 here are, these are example numbers, by the way. These are example numbers calculated on the distributions that are indicated below them, okay? But generally speaking, the mu can be a vector having any values, and the sigma can be a matrix. For sure, it is 2 by 2 if you are speaking about data of 2D like this. So it is 2 by 2. It is symmetric for sure, but it can have any values, okay? So what is the meaning of the value here? If you can see my pointer, it is the covariance of it is the variance of the first feature, okay? The variance is the square of the standard deviation. That other element in the diagonal here is the variance of the second feature, okay? What about the elements that are off diagonal here? Again, it is a symmetric matrix, so you should have the same value of diagonal, and that value is representing the covariance between the two features. If it is a positive number, it means that the two features seems to have a positive correlation, which is the case in our example, by the way, when the majority of it is quite often in our data set when we find a player with a high height value, usually his weight is high. And when the height is getting smaller, we tend, based on our data, to find that the weight is getting smaller. So we have a positive correlation. This can be indicated in the covariance, as a positive covariance number. Okay, so we can from a data points like this, we can estimate the mu value, and we can calculate the covariance matrix. We have an equation to calculate the variances and the covariance. For a data that looks like this, the covariance should be positive. If the data is less scattered, the variance should be small. If the data is centered around 1, 1, the mean should be 1, 1, 1. If it is centered around 0, 0, you will find that the mean value you calculate from the equation will be equal to 0, 0. Okay, so from data like this, you can calculate the mu vector and the sigma or the covariance matrix. And if you try to visualize the function f, which is a function of mu and sigma, okay, which is taking a data point from mu, it will look to something like this. So the z-axis here is f, okay, and each axis here is representing one feature of the two features we have, and z or f is representing the probability of that point in space to happen given my my collected data. Okay, because actually I have created this distribution from data. Okay, so it should give a high value whenever I substitute with a value that was similar to the collected data, a value that happened a lot in the collected data. Okay, to conclude, we have some points. From them, we calculate the mu vector, the sigma matrix, okay, the covariance matrix, and we can substitute by mu and sigma in this equation. This equation, it takes x. X is any point in this 2D space. Okay, so small x here corresponds to a vector of capital X and capital Y. And once you give it x and y, you give it a point in space, it gives you back the probability of that point of space. If you give x equal 4 and y equal -4 here, you expect to find f equal very small number, because this point did not happen a lot in your training data. Okay, but if you start to choose an x and y toward this center, you start to get more value. Okay, this is how the function f looks like in 3D, and if you project it in from top view as 2D, given 3 examples of mu and sigma, you will find that the more correlation you have, the more narrow and diagonal will be the Gaussian distribution in 3D space. Sorry if I'm discussing this very quickly, but I assume that you are already familiar with Gaussian distributions in 1D and in 2D. And if not, I wish my brief description will help you become familiar with it. Okay? So you might use a Gaussian distribution, a single Gaussian distribution, to model data coming from a single cluster. But if you want to do clustering, so most probably your data is belonging to several clusters. Okay, so assume that you pick up the right k from the beginning. So assume that the true k is set to 3, for example, and you were lucky to choose k equal 3 for your GMM. So the GMM will create 3 random Gaussian distributions in the space, and it will try to fit your multi-class data, or your data that is composed of 3 clusters, to your 3 Gaussian distributions. And eventually, each Gaussian distribution of the 3 will fit one cluster out of the 3. Okay, so you want to fit your data using an equation like this. So if your data is coming from a single cluster, you need to fit it using something like this, a single Gaussian distribution. But because we have data that's coming from several clusters, we need to have k normal different Gaussian distributions. Each one has its different mu k and different sigma or covariance matrix k. Okay, and we want to fit our data to the summation of these 3 or k Gaussian distributions. And in order to have the output as probability, you need it to be at maximum equal to 1, and you need the summation or the integration over this equation over the domain of x to be equal to 1 as well. So we need to multiply each Gaussian distribution by a mixing coefficient or a weighting factor, which is by k. Okay, so at the end of the day, we have data that we want to fit to p of x. Okay, x here is your feature, your input feature. So if you have data like this and you choose k equals 3, hopefully with time you will find that your 3 Gaussian distributions that you started randomly will settle around your data like this, to achieve again an outcome that looks like what we wanted to achieve from the beginning. For sure, if the addition of these 3 distribution, if you have 3 distributions like this, for example, the addition for them, b of x, after multiplying by the mixed coefficient, gives you a distribution like the dark black one here. So this is can be an example for your b of x. So let's now describe how the Gaussian mixture model is working to cluster your data. We start from random Gaussian distributions. How many? Depends on the value of k. Let's assume k is equal to 2. So we randomly initialize in terms of location and in terms of shape 2 Gaussian distributions, and we repeat until convergence the expectation maximization algorithm. Okay, we will talk about convergence later on. Let's describe what's happening in the expectation step and the maximization step. During the expectation step, actually, we cluster the data given the Gaussian distributions we have reached. We soft cluster the data. So for each point, we give it a weight to be assigned to cluster 1 and another weight to be assigned to cluster 2. And the weight that this point should be assigned to cluster 1 is obtained by substituting by this point in the first Gaussian distribution. This is the first weight. And by substituting by the same point in the second Gaussian distribution, we get a different number, which is the weight that this point is a member of the second cluster. Okay? So initially, the clustering performance will be very bad because the Gaussian distributions are chosen randomly so far. So we will improve the Gaussian distributions based on our soft clustering decisions. So we will re-estimate the Gaussian distributions, or we will change its location and their shapes based on what we did in the expectation step. So for each Gaussian distribution, we will estimate its mu vector, its mean vector, its covariance matrix, and its mixing coefficient in a way that makes our Gaussian distributions perfectly fit our soft clustering decisions. Okay, and so they will adjust, and after they will adjust, you will do soft clustering again. You will calculate new weights, and given these new weights for all the points, re-estimate the Gaussian distributions so they best describe your soft clustering, your weights of membership to each cluster. Okay, I'm not very interested about. I'm not interested to give you the details regarding how can you re-estimate the parameters of a Gaussian distribution to fit a cloud of points with weights like that, but I would like the concept to be clear in your mind. So assume that at some iteration you will find that the Gaussian distributions are not changing anymore. So accordingly, your soft cluster result will not be changing anymore. This indicates that convergence happened and you should stop your algorithm. Before speaking about convergence, let's very quickly describe the expectation maximization algorithm graphically. So you start from data like this. The data is having the same color because we don't know the label. And you start from two random Gaussian distributions. K is equal to 2. So let's say that this is the first random Gaussian distribution and this is the second one. What is this circle? This circle is a plane that intersects our 3D Gaussian distribution. Okay, our Gaussian distribution is 2D. So to visualize it, you should draw it in 3D. But if you cut it using a horizontal plane, you will have a circle or an ellipse. You will get a circle if the covariance is equal to 0. You will get an ellipse if there is a covariance, whether it is negative or positive. Okay, but at least this circle is telling us that the center or the mean of the first Gaussian distribution is here, and the second circle is telling us the mean of the Gaussian distribution is here, and the width or the diameter of the circle is telling us how much the variance of the Gaussian distribution is. Okay, it's a good idea to cut both the distributions using the same horizontal plane. Okay, where the equation of the horizontal plane is z equal a constant value, and you should use the same constant value when you cut the two distributions. Okay, But at least you know that we have a distribution here, we have another distribution here. Let's do soft clustering. Let's do the expectation step. So according to the expectation step, all of the points here will be assigned more to the red Gaussian distribution. And you will find that there are strong red points. The color here is indicating a heat map representing the weight. So the weight of being assigned to this Gaussian distribution is much higher because it is near it. So for example, when you substitute by this point in the red Gaussian distribution, you get a weight of 0.9. But when you substitute by the same point in the blue Gaussian distribution, you get 0.2 or 0.1. So it is more assigned to the red Gaussian distribution. It has higher weight, so it is more red. And the less you start to have confidence, the more you will find the point color between red and blue. And the clear blue is indicating that it is more strongly classified into the blue cluster. Okay, let's do the maximization step. According to this soft clustering, we want to adjust our Gaussian distributions or the mixture of Gaussians in order to fit this soft clustering results. Okay, this is the step that I'm telling you. I'm not very interested that you know the math behind it. But in order to fit these colors, these weights, the distributions will find that they should adjust themselves like this. So the mean value of the red distribution will be here, and it will start to have a very high positive correlation and less covariance like this. And this is how the blue Gaussian distribution will be adjusted. What about the second maximization step? It will be like this. This is the fifth maximization step, and this is number 20 maximization step. You will find that 21, 22, at iteration 23, it is almost the same maximization step, which indicates that convergence happened, and this is the clustering outcome that you can achieve. For each point, you have a confidence to be assigned to cluster 1 or cluster 2, and the color here is indicating this confidence. You will find that most of the points are pure red or pure blue, because here the convergence was very good. So you will find the points are either strongly red or strongly blue, except for the points in the middle here. You might start to find that the confidence is not very high. Okay, so how can we measure if convergence happened or not? What is the aim? The aim is to have a mixture of Gaussians that fit my data. Okay, so initially you start from a Gaussian distribution that does not fit, a mixture of Gaussians that does not fit your data. So assume that you have data like this. It is 1D data. So you have data that looks like this. Okay, coming, let's say, from 2 clusters. And initially you have a very bad mixture of Gaussians. You have, let's say, k equal 2 in our example. So you have a bad 2 Gaussian distributions at the beginning. Let's say one is here. And maybe another one is here. Okay. So where is the mixture of Gaussians? This is the summation of them. This is the mixture of Gaussians that we have. Okay. So this is B of X. If you want to calculate the likelihood of this mixture of Gaussians, the likelihood is actually some metric that tells you how much this Gaussian distribution is fitting your data. It is very simple to calculate it. You very simply substitute by each point in your distribution. So this is the first point, substitute here, you get probability here. What about the second point? Substitute here, you get another value for b of x. The third point, and so on for all your data points. For this point, for this point, for this point, for this point, for this point. You have how many numbers? You have numbers that are equal to your points, and you substitute here by doing something like this. So b of x1 times b of x2 and so on. So if you multiply all of these probabilities, you get the likelihood of having your distribution modeling these data points. And we do multiplication because we assume that these points are identically independent samples, okay, IID samples. So eventually you will find that you have a very small value here. Let's say, for example, 0.1, because you have very small numbers here. We know that the max is the integration of this green curve over all the possible values of x is equal to 1. So we expect to have a height here of something like 0.3, not more than that, because it's a PDF, it's a probability density function. So we might eventually calculate L, find it equal to 0.1 something like this. Okay, so after convergence, we wish that our two distributions fit the data much better. So the first distribution become like this, and the second distribution become like that. So the mixture of the two distribution is something like this. Okay, so if you calculate L, the likelihood for the new distribution, you will find that you will substitute by this point in that red curve this time. So you tend to have higher values. Okay, so you tend to have higher values, higher values, higher values for all the points, higher values, higher values, higher values, higher values, higher values. So when you multiply this time b of x1 times b of x2 and so on, you will get a higher value, let's say of 0.4 or something, 0.3 or something like this. For sure, I'm here just giving an example. The numbers will not be that high. Practically, it will be very much smaller than this. But relatively, the likelihood of the red curve, the red mixture of Gaussians, is much higher than the likelihood of the green curve, right? So the likelihood is as a strong indication of how much my Gaussian distribution or mixture of Gaussians are fitting my data. Okay, so I can calculate after each maximization step, I calculate the likelihood, and during the first iterations, I will find that the likelihood is increasing significantly, and after some iterations, I will find that the likelihood value is increasing with very, very small threshold. So if I find that the improvement is very small, smaller than a predefined threshold or something like this, I say convergence happened and I stop the algorithm, because the Gaussian distributions are not changing significantly anymore. Okay, so it is very computationally expensive to calculate b of x, because especially if you are going to do this iteration after iteration and for many points. Okay, because to calculate the likelihood, you rely on multiplication, and multiplication is not as efficient as addition operation computationally. So we might, instead of calculating the likelihood, we might prefer to calculate another function which is monotonically increasing with the likelihood. So instead of relying on the likelihood, we will rely on the len or the log of it, the log likelihood. Okay, and if likelihood is increasing, the log of it is increasing. So it is safe to rely on the log likelihood instead of calculating the likelihood. Okay, so the likelihood, log likelihood will be increasing iteration after iteration, and you should stop when you see the increase is very small. Why did we use the log, not the likelihood directly? Because it's computationally expensive. It is computationally less expensive, because all of the multiplications will be transformed into addition. And so let's take this pen. So this is b of x, and this is b of x. So now we calculate log b of x. So you will find that instead of actually b of x is composed of the multiplication of several, maybe we can choose another color. So b of x is the multiplication of b of x of each point, right? And this is b of x for each point. And instead of multiplications, instead of all of these multiplications, okay, you will have n additions instead of n multiplications. N here is the number of points you have, and the len here goes inside. And when you apply the len on n, or the normal distribution equation, which is having exponential, it will be very computationally inexpensive. It will save you lots of unneeded computational power, because len exponential anything is anything. Len exponential 5 is 5, so you will not need to do the exponential calculation for all the points, so many iterations. Okay, so it is very computationally efficient to use log likelihood instead of the likelihood, and it is safe to use it as long as it is monotonically increasing with b of x. So this is b of x, and this is len b of x. Another advantage of using the log likelihood as your convergence criteria is that b of x values will be generally very small numbers, and when you multiply very small numbers, it will be even more smaller, and you need to store them somehow in order to compare them, and you will need very high floating point precision in order to keep track of your very small numbers. But while you convert to log likelihood, you will find that these very small fractions are starting to give you big numbers much bigger numbers in absolute. And this is why it is even more computationally efficient to rely on the likelihood and not the to rely on the log likelihood and not the likelihood. Okay, so very simple trick, just to use the log of it, saved so many things for us. By the way, the part from here is unpractical, because we know that p of x, the maximum value of it is equal to 1. This is another visualization for how the k-means iterations are happening. So this is the first iteration. You start from random k-means, and by time they start to converge to a very good representation of your data that allows you to do very efficient clustering. So let's very quickly go for a workshop to learn how can we use Scikit-Learn library to implement Gaussian mixture models. So reconnect to our Google Colab. Let's upload a notebook. So I'm doing some imports that I'm going to need later on. By the way, this code is adapted from this very nice tutorial. The link will be here for you to investigate the tutorial more. It's very useful. So there is a very nice class in Scikit-Learn that allows you to generate data that looks like blobs. It's named make blobs from Scikit-Learn dataset sample generator. You specify the number of samples, the number of centers, the standard deviation of points around each center, and a random state to be able to reproduce the results again and again. After this, I cluster the data, which is composed of 400 samples using k-means. You already know how to do this. So I fit a k-mean model, and I predict the same data that I used for training the model. I predict how the k-means will cluster them or classify them into the different clusters, and according to the labels I obtain, I color the outcomes. Okay, so this is the result for the k-mean algorithm. By the way, and let's try to run this. If, for example, you change the random state here, you will find that I will end up having different points configuration. So it is different point configuration. This is a function that I use to draw a circle around each cluster center. It's a very simple function. Let's run this cell because we are going to call this function later on. And here I call it plot k-means. So it draws a circle around each cluster. And actually, I will do matrix multiplication. I will multiply my 400 by 2 matrix holding my 400 2D data by a random matrix 2 by 2, which means that I'm doing projection for my data. Okay, I'm doing projection to until I start to see my data is skewed in order to check how Gaussian of mixtures will be able to handle this data. So let's see how this projection will do to our data. So yeah, the data is skewed, as you can see, and you start to see that k-means is not solving it very well. Here we have some samples that are classified as the green, okay, but they should be classified as yellow class. And here also we have some yellow that is coming from that class and the green class. So k-means is not performing well on the data after projecting it somehow to make it more challenging. And the reason why is this is that the k-means algorithm is assuming that the clusters are spherical or circular in our 2D case. So let's train a Gaussian mixture. So from Scikit-Learn mixtures subpackage, you import the Gaussian mixture class. You instantiate it using by giving it the number of components, the k value, and you fit it on your data. Okay, once you fit it on your data, you have your model, and you can use this model to predict or cluster any data. And as usual, we use the same training data as test data. So we predict on our training data, and given the label, I visualize them. So let's run this code. So this is how our mixture of Gaussian is doing the classification on the original data X before projecting them, before making the problem more challenging, because after making it more challenging, we store the challenging data in X spreadsheet. So let's try how. Okay, this is no need to do this. Okay, this is another function that I'm going to use to visualize the result for the mixture of Gaussian by drawing ellipses. And here I'm going to try again the mixture of Gaussian having 4 components on my X data. Okay, so plot GMM is calling the predict function. This is what I'm doing above. So this is something we did before, but now we will see the circles or the ellipses. Yeah, we didn't run this cell. We need to run it because we are going to call the API plot GMM. So let's run this again. So this is how the GMM is clustering the normal data, the less challenging data. And what about the challenging data? Yeah, it's classified much better than the k-means algorithm. Now we have these points classified as yellow. This is the result from the k-means algorithm. And this is the result from the mixture of Gaussians algorithm, much better. Okay, let's try more challenging pattern. You have make moons API. It's a very nice API. You can generate data that looks like moons. And how many moons do we need? By default, they are 2. And how many noise do we need? And random state for reproducibility. Let's run a Gaussian mixture on this data. Let's cluster them using GMM. That's having k equal 2. So it's very challenging for Gaussian mixture of Gaussians to classify or cluster this data given k equal 2, because you cannot fit this data into 2 Gaussian distributions or a mixture Gaussian of Gaussians having 2 Gaussians only. Okay, but if you increase the number of components to 16, you will find that you can very easily fit data like this. Each ellipse here is representing a cluster or a class. Okay, so again, it is not a solution to the problem, but at least this is a better clustering outcome than this performance. Okay, and for this, yes, we have much more clusters than 2 clusters. We have 16 clusters, but at least we have 2 Gaussian. At least we have some Gaussian distributions that fit our data. Okay, what I want to say here is that you might k might constrain your Gaussian distributions not to fit the data from the start. A data like this from the start, if you want to fit it using 2 Gaussians, you will not be able to fit it. But if you want to fit it using 16 Gaussians or more, you will be able to easily fit it. If you try k equals 3, I think the performance also will be very bad. Yes, we need to run the cell of generating the moon data. We didn't run it. Let's run it. And let's try k equals 3. It should be bad, not good. What about x equal 10? Much better. Okay. So by this exercise, we conclude the mixture of Gaussians, and we should now talk about how can we select the right clustering algorithm out of the 4 algorithms that we have discussed. Okay, we have actually more than these 4 example clustering algorithms, but these are, from my point of view, the most famous and the most used algorithms, and all of the other algorithms you will see in literature or anywhere will be lying in one of the 4 categories we have discussed. It's either distance-based, dynasty-based, soft clustering, or hierarchical clustering. Okay, so let's open the laser pointer. So if you want probabilistic assignation, there is no option except GMM, soft clustering. So you reject all the other options. If complexity is very important for you, if speed, runtime speed is very important to you, and space complexity as well, the RAM of your machine that will execute the algorithm, you should reject hierarchical clustering. We discussed the complexity of it, and it is even more than quadratic complexity. So you should reject hierarchical clustering technique. Okay, and if K is hard to determine from the beginning, so you reject K-means and GMM because they require K. If you need to reject outliers, if you need to detect noise, you should rely on DBSCAN because it detects noise, or GMM because noise will be assigned with very small probabilities to the clusters. Okay, so you know that the assignation is very small based on some threshold, so you assign these points as noise. If you don't want any parameters, you should rely on hierarchical clustering, and for sure, K-means requires the K parameter, DBSCAN requires the epsilon and the sigma, GMM requires the K parameter, so you should avoid them. This is rough guideline that might help you choose the right clustering algorithm for the problem in your hand. And this is a nice figure I borrowed from Udacity that benchmarks actually the K-means clustering versus DBSCAN versus single link hierarchical clustering. As you can see, hierarchical K-means is working well in this case and that case and that case, but it's doing very bad with overlapped data like this. DBSCAN, density-based clustering methods, can very easily tackle these patterns, but actually it does not perform well with this case because the choice of the epsilon and the minimum number of points might be not very easy in some cases. But as you can see, hierarchical clustering is also working well with these two cases like DBSCAN, but also works well or better at least in this case. So again, there is no single algorithm for clustering that is better than the other methods in the absolute. Each one has its strength points and weakness points, and I wish they are more clear in your minds from our discussions. So if you applied a clustering algorithm and you want to judge whether the output is good or not, and you can do this visually, you can visualize the outcome like what we did here, and based on it you can decide. But most of the cases you have complex data patterns, and you have high dimensional data that you cannot visualize in 2D, and it's very hard to tell visually whether the performance of clustering is good or bad. This is why we are going to discuss the clustering validation methods, and we want to create some methods that give us some numbers that tell us how much the clustering algorithm is separating the data. This is the first criteria, and how much separating the data coming from different clusters, and how much it is not separating the data of the same clusters, of the same cluster, how much each cluster is kept compact. So we need to test separability of the different clusters and compactness of the data points coming from the same cluster. There are two scoring methods that we are going to study. There is the external indices and the internal indices. We use the external indices when the data is labeled, when we have a ground truth that we can compare the outcome of classification process with or versus this ground truth, or in the majority of cases we use unsupervised learning because we don't have labels. So if we don't have labels and we want to judge the accuracy of clustering, we should rely on internal indices. There are several examples for external indices that you can use to do clustering validation, like adjusted random score, NMI measure, Jacquard, many things. Okay, most of them are implemented in Scikit-Learn library. One of the indices that we are going to cover is the random score. It's an index that gives you a value from 0 to 1. 1 means that the outcome of the clustering is very good. 0 means that it is very bad. And actually, the RI index is calculated like this. It's equal A plus B over N combination 2. N is the number of points that we have in our data, and A is the number of pairs in my data that lie on the same cluster, and they should. Okay, so in the true clusters, they also lie on the same clusters. What about B? B is the number of pairs in my data that lie in separate clusters, and when I check the true ground truth clusters, I find that they should lie in different clusters. Okay, and N combination 2, sorry, N combination 2 is actually the total number of pairs, of possible pairs that I can have in my data. Okay, so if the clustering does not agree at all with the ground truth, you will find that Ri is equal to 0. If you reach a clustering that is exactly the same as the ground truth, you will find that Ri is equal to 1. But one big problem with that Ri index is that two random clustering output or two random clustering configurations does not necessarily give you a constant value. So if you for example do random clustering like this, if you can see my pointer, so this random clustering is giving you Ri value, which is toward this 0. And if you do random assignment, a different random assignment, you will get a completely different Ri value, which it is small as well, but it is completely different. To adjust the Ri index to correct for this effect, there is another external index or metric that's called the adjusted random score that eliminates this downside effect. So this is the paper that describes this algorithm. If you want to go back to read details how the adjusted Ri index is working in detail. Okay, so if you have this ground truth, if you apply k-means several times, you will find that this is the ARI at each time. Okay, so the higher ARI or RI, the better you can tell the clustering algorithm is performing. So very quickly, we have a workshop regarding this, how to use the adjusted random variable in Scikit-Learn library. And we will use the iris varieties dataset again, and we will try to visualize the outcome of the clustering algorithm, which is challenging because if you remember, this dataset is composed of 4 features, so it is impossible to visualize it in 2D or 3D. This is why we will rely on some library. Let's open the workshop. So we will rely on the Seaborn library. It's a statistical data visualization library, and you can call the API per grid. You can give it your dataset after loading it from Scikit-Learn library. Okay, you can give it some parameter, and you have very nice visualization like this. You get for each feature, which is, for example, the first feature is the Sibal lens. It will draw this feature for you against all the other features. So this is the first feature against itself. So it makes sense to have it like a line like this. And this is the first feature versus the second. This is the first versus the third, the first versus the fourth, and so on. The second row here is drawing the second feature versus each other feature. So this is the second feature versus the first feature, so it is equivalently the same figure as that figure. This is the second feature with itself. This is the third. This is with the second feature with the fourth feature, and so on. And the colors here are the labels, or the ground truth labels. Okay, so here I'm trying to visualize the ground truth clustering outcomes that optimal clustering algorithm should obtain. And afterwards, I try to create a k-mean, and I fit predict the k-mean. We can do the fit and the predict at the same time together in the same step, instead of fitting a model and having this model calling its API of predict. We can fit predict at the same time. So we have some predictions, and I visualize them. So these are the k-means results. If you compare them with the ground truth, you might find that it is good. You might find that it is bad in some aspects. But anyway, it's very hard to compare visually all of these figures with all of these figures. This is 4D data. So imagine if you have 100D data or something like this, which is in industry something that is normal to deal with 100D data or something at this scale. So here I'm creating another clustering algorithm, Gaussian of mixtures, nothing new here. I have it, I fit it on my data, then I do predict, and I visualize the result using the Seaborn library. So this is the outcome of the GMM clustering algorithm. Okay, and again, it's very hard to compare it against the k-means, and it's very hard to compare it against the ground truth. This is why the adjusted random score becomes very handy tool. So adjusted random score is imported class from Scikit-Learn Matrix subpackage, and you can give it, you can call it just like this by giving it the ground truth and the predictions. And here I give it the ground truth and the predictions from the k-means, because I store the predictions in a dictionary, and I print the score. And afterwards, I calculate it for the predictions of the GMM versus the ground truth as well. So the k-means is giving you 0.7 or ARI, and the GMM is giving you 0.9, which is indicating that the GMM result is better, instead of having the need to compare it with the ground truth and to compare the k-mean with the ground truth to achieve this conclusion. This is why it's very important to have clustering validation. Okay. So let's talk about internal indices. Most of the time, we don't have any ground truth. We have data that is unlabeled. So we have lots of internal indices to use, the silhouette index, the dune index. Most of them are also implemented in Scikit-Learn library. Let's study only as an example the silhouette index. It gives you a number from -1 to 1, like the adjusted random score. And for each sample, you calculate its silhouette index. For each sample point has a silhouette index. Okay, so for a point pi, it has silhouette index si. Si is equal bi minus ai over the maximum of them. Which one is bigger? Okay, so what is pi? Sorry. So what is pi? Pi is the average distance with the nearest cluster point. So the point pi is in some cluster, and this is the cluster that is nearest to that cluster. Okay, so we will calculate the average distance between our point pi and all the points of that neighbor cluster. Okay, this is pi. And what ai? Ai is, this is the point, and this is the same cluster points. So we calculate the distance from pi and the points in the same cluster. Okay, so normally pi should be higher than ai. Okay, so if pi is 6 and ai is 3, so 6 minus 3 over 6. Okay, which is 0.5. So you will find that it is equal to 1 if the sample I is, or the point I is well clustered and assigned to the right or true cluster. It will be equal to 0 if the sample is equally far from two different clusters, and it will be equal to 1 if the sample is misclassified. So the Salouhat index for the whole clustering algorithm is the average of SI for all the points you have in your data set. As example, this is the data. This is an example for a data we have, and we run k-means using a different value of k. For sure, the true k should be equal to 3, but we don't know beforehand. So if k is equal to 2, this is the result, and this is the Salouhat index or score, and k equals 3, k equals 4, k equals 5. You will find that the best result visually corresponds to the highest Salouhat score value of 0.8. So it's very handy tool. If you don't have ground truth, you can quantitatively judge the quality of your classification, your clustering algorithm. But again, you shouldn't trust it 100%, because it is not always reliable. For example, in this case, I run different clustering techniques, complete link, word, DBSCAN, GMM, k-means on the same data, and it seems that the DBSCAN is the best, while its Salouhat score is the worst, actually. So again, it's something that is helpful, but it is not always reliable to rely on it. So try to maybe visualize the data, and it is, if it is multidimensional, try to have a look on like we did using the Seaborn library by how to visualize multidimensional data, at least to have a look on your data. So don't blindly trust the Salouhat score. It's helpful, but don't blindly trust him. And especially if you deal with DBSCAN, the Salouhat index is especially not suited for it, okay? Because actually the Salouhat index or the Salouhat score is assuming that the clusters are separate bulks, okay? So do we have better techniques to validate data that is more suited to the DBSCAN algorithm? Yes, there is a very nice paper appeared in 2014 named Dynasty-based clustering validation. It tries to tackle this problem, and I encourage you to read more about this paper. Last thing that I would like to discuss with you is that you can rely on the Salouhat index to calculate the value of k. So you can try different values of k. You can run the clustering using k-means k equal 1, then run it again with k equal 2, k equal 3, and so on. And each time you calculate the Salouhat index. And because the Salouhat index is very suited to data that can be solved using k-means, you can trust it. So you can draw this graph, and you can pick up the k that maximizes the Salouhat index. So that was everything I wanted to share with you regarding the unsupervised learning topic using clustering. I wish it was useful and enjoying to you. Thank you so much. Let's stop sharing screen, and I wish you have a nice day, and see you next week. Goodbye. Bye-bye.